Hey folks, Mr. Bucko here. I'm going to talk to you about 12.6, which is on the side similarity theorem for triangles. So I'll describe what that is, go over a couple of examples, and let you be on your merry way with some problems to take a look at. So first of all, the side similarity theorem for triangles says that if three sides of one triangle are proportional to three sides of a second triangle, then we can say the triangles are similar. So the one thing we want to make a note of here is what this word proportional means. Proportional means that there is a multiplicative relationship between the values. And in this case, it has to be all three sides have to have that relationship. So of these three triangles, two of them are similar. We're going to decipher which two are similar based on determining which sides are proportional. So we take a look at this first one. This first triangle here has values of 7, 4, and 9. The second one has 2, 3.5, and 4.5, and the last one is 11, 6, and 9. So if we look at these two, someone might say that the first triangle here and the last triangle are proportional because if we take 7 and if we add 2 to it, we get 9. If we take 4 and add 2 to it, we get 6. And if we take 9 and add 2 to it, then we get 11. That sounds reasonable. These are not proportional, even though there is that relationship that we just added 2 to each of the side lengths. Proportional means that that relationship has to be multiplicative. We have to multiply something by each of these side lengths to get the resulting side lengths of the other triangle or similar triangle for it to be similar. That's not the case. 7 times whatever is 9 is not the same thing as 4 times whatever is 6, and so on and so forth. However, if we take a look at the first triangle with respect to the second triangle, we may notice a multiplicative relationship here. And if I go backwards, it might be a little bit easier to see. If I take this 3.5 and multiply it by 2, I get 7. If I multiply 4.5 by 2, I get 9. If I multiply 2 by 2, I get 4. So these three side lengths here are proportional to these three side lengths by a factor or a ratio or a magnitude of 2. So we would say then that the first and the second triangles are similar based on the side similarity theorem. The three sides of this triangle are proportional to the three sides of the other triangle, because if we take these three sides and multiply it by 2 in this case, we get the resulting three sides of the other triangle. So that's what the side similarity theorem says, and we have a couple of examples to take a look at with respect to that. So here we have two triangles, and we're going to just determine if these triangles are similar. And since we're given three side lengths in each of these triangles, we can just match up and see if they are all proportional, if there's the same value from one that gives us the other values in the larger or smaller triangle, depending upon which way we go. So what we can do here is we can match up the shortest to the longest sides in each of the triangles and then take some ratios here. So these ratios are what we would suspect would be the ratio of similitude if it did exist. So let me talk about where this sequence of numbers comes from. The 3, 6, 8 come from the smaller triangle and ordering them from smallest to largest. So 3, 6, 8. Smallest side, next smallest side, 8 is the largest. That's where the 3, 6, 8 come from. These denominators come from the shortest to longest sides in the larger triangle. Because if these triangles are similar, 3 has to match with 8 because those are the two shortest sides. 6 has to match with 16 because it's the second longest side, and 8 would have to match with 64 over 3 because those are the longest sides. If they're similar, which we're investigating if they are or not, those things have to be true, that those things have to match up. That's where this relationship comes from. 3 to 8 would be the same relationship as 6 to 16, would be the same as 8 to 64 over 3. So what we have to do is investigate whether or not these three fractions that we have here are the same, because if they're the same, then they're proportional, then they're similar. So let's take a look at the first pair. 6 over 16 right here is equal to 3 over 8 because we can simplify that. 6 over 16 can be reduced to 3 over 8. So 6 to 16 is the same relationship as 3 to 8 because they're equivalent fractions. That one's not too bad to identify and kind of see why those might be the same. Gets a little bit difficult though because we have 8 over 64 over 3. How do you like that? A compound fraction. So what I like to do when I see this mess is I like to kind of break down exactly what does this mean. 8 over 64 over 3. Well, when I see that, I say 8 divided by 64 over 3. This fraction bar right here can just be treated as a division symbol. So we have 8 divided by 64 over 3. This I can simplify. I remember how to divide fractions, and what that protocol is taking the second fraction, taking the reciprocal, and then multiplying. So 8 divided by 64 over 3 is the same thing as 8 times 3 over 64. And then I can multiply these two things because I can just do 8 times 3 and then 1 times 64. Where do I get 1 from? I change 8 into a fraction, and then I multiply across. So 8 times 3 over 64 is going to be 24 over 64. 24 over 64 is a fraction that can be reduced. I notice that 8 goes into 64 and 24. Therefore, that can be reduced to 3/8. So in other words, this fraction right here that is a total mess is equivalent to 3/8, which is one of the ratios of one of the other pairs of side lengths in the similar triangles, which we can now indeed say that they are similar because all three of these ratios are all the same. So as a result, because all the ratios are equal, all three of these fractions are the same value, the triangles are similar due to the side similarity theorem. One more example here. Let's see that that's right. These two triangles and some side lengths are given, as you can see here. The angle measures are approximations to the nearest tenth of a degree, just 29.8, 55.2, so on and so forth. That's all that's saying there. So let's say that FED this means similar to GOV. They're not congruent. They're not the exact same size, but they are similar. We want to find out, well, what is the ratio of similitude? If we kind of match this up, find the ratio of similitude, we have to match up corresponding sides. So we have a missing value here in GO. We have all the values of FE and FE, E to D, and D to F. So what is the ratio of similitude? Well, we got to match up corresponding sides. So let's take a look at FE. FE in this triangle would match or correspond to GO. So FE5 matches to GO. Well, GO does not have a value there. And since GO does not have a value assigned to it, we can't determine the ratio of similitude if we're going to look at the relationship of FE to GO because there's no value for GO. So let's take a look at the next segment here. We have ED. ED in the first triangle corresponds to OV. ED corresponds to OV. So 3 corresponds to 1. There's your ratio of similitude right there. ED, 3 to 1. 3 to 1 is the ratio of similitude. Or you could say it's 1 to 3. You can go both ways. It doesn't matter. The 3 over 1 is if you were going to go from the smaller triangle to the larger. The 1 to 3 is what you would multiply if you're going to go from the larger sides to the smaller side. So either one of these two is okay for the ratio of similitude. It's just a matter of which triangle are you going to and from and vice versa. And it can kind of be flipped and flopped and so on and so forth. So it doesn't really matter which one of these two you use. They both say the same thing. And we can verify that with the last line segment, DF. DF corresponds to VG. DF corresponds to VG. So 6 corresponds to 2. 6 over 2, or 2 over 6. Well, 6 over 2, 2 over 6, is the same exact thing as 3 over 1 or 1 over 3. So it doesn't really matter which two sides you pick, but you need to have corresponding sides that you actually have values for in order to find the ratio of similitude. So the ratio of similitude of these two triangles is 1 over 3, or 3 over 1, or just 3. So since GO is not there, what would make these triangles similar? Well, we can find GO now because we have the ratio of similitude. We have the ratio of similitude, which is 3/1, and we have the side length FE. So what are we going to do to FE, the side length FE, which in this case is 5, to get that missing side length GO? Well, we're going to take 5, and we're going to multiply it by 1/3. Why 1/3? Because we're going from the larger triangle to the smaller triangle. We wouldn't multiply 5 by 3. That would make this side 15, and that doesn't make any sense. That can't be 15. All of these side lengths are smaller. So we're going to do 5 times 1/3, and 5 times 1/3 is just 5/3. So the length of GO has to be 5/3 if these triangles are similar. How about the last angle of, or finding all of the angles of GOV? I say the last angle because there's only one we need to find out. If we want to find the measure of each of these angles here, we have to kind of refer to this triangle here, and we have to recall that if figures are similar, their angle measures do not change. Their angle measures are exactly the same. If you change the size of a figure, angle measures don't change. They stay exactly the same. We have two angle measures here. We have F and D. Well, where does F go in the smaller triangle? What does F correspond to in the smaller triangle? Looking at the picture, we can maybe take some guesses. We could be right or wrong, but if we want to know for sure, we take a look at the similarity statement. FED is similar to GOV. So angle F has to correspond to G. E has to correspond to O. There's E, there's O. And then V has to correspond to D. So D and V correspond. So we go to F and G. Well, if F is 29.8, angle G has to be 29.8 because they're corresponding. Then we take a look at angle O. Angle O has to be 95. Where does 95 come from? I don't see 95 here. 95 comes from the fact that we know that all of the angles in a triangle have to add up to 180. 180 minus 29.8 minus 55.2 is 95. So angle E has to be 95, but angle E corresponds to angle O, so angle O has to be 95. And then as a result, angle V has to be 55.2 because D corresponds to V. D is 55.2. O has to be 55.2 as well.